Hey, hello everyone, and welcome back to Candle Seminar. And today is another internal seminar by our Prashant. Prashant will tell us about dual perspectives on quantum Hall Plateau transitions.
Okay, thanks Arjuan for the introduction, and thanks everyone for coming to this talk. This is somewhat of an old work. Most of this work was done during my PhD, but I thought I would resurrect this because this will form a decent part of my future work. And as you will see, there are many unresolved things, and I have several projects that are coming up in future. My collaborators are my PhD advisor, Sri, Mike Mulligan, who is at UC Riverside, Yongbek Kim in University of Toronto, and two students at Stanford University. Let me start with the very broad motivation for why we want to study this topic. I'm sure many of you are familiar with topological phases of matter. These have been an intense area of study in the past 4 decades or so. The reason we are interested in topological phases of matter is that they are beyond the paradigm of spontaneous symmetry breaking, and they are a different way of classifying phases. These phases are characterized by properties such as topological indices, ground state degeneracies, fractional quasiparticles, long-range entanglement, edge states, and so on. Although these states can arise, some analogs can arise in classical systems, but in quantum physics, we have complex and multi-component wave functions, which leads to many interesting topological phases. In the same vein, the phase transitions that involve these topological phases they also offer a distinct class of critical phenomena than the conventional spontaneous symmetry breaking ones. One of the examples or one of the reasons for this can be seen by the fact that these transitions involve topological terms, and if we do a Wick rotation, t goes to minus I tau, the topological terms remain imaginary. At least the one I would talk about in that case, these terms remain imaginary. And if you think of a classical statistical system which has a positive Boltzmann weight, it's difficult to think how these topological phase transitions can arise in such systems. So these are very much quantum mechanical. And as a result, what is interesting about these topological phase transitions is that we have emergent excitations such as vortices, gauge fields, and as a result of quantum mechanics, we have interesting quantum interference effects. I will talk about some of those quantum interference effects, at least at a high level in the remaining part of the talk. How about these quantum Hall Plateau transitions? I will give more details in a bit, but these are transitions between different quantum Hall plateaus. And what are these quantum Hall plateaus? If we take a 2+1 dimensional system, apply a perpendicular magnetic field, by the way, these are electrons, and we measure Hall resistivity, we see these plateaus, like Hall resistivity stays fixed at some value for a range of magnetic fields, and then it suddenly jumps to a different plateau. And the transition between these different plateaus in Hall resistivity, that's the quantum Hall plateau transition. And these are one of the very nice, very extensively studied topological phase transitions in experiments. However, a complete theoretical understanding of these transitions has been elusive. The reason is that a complete theory of these transitions will involve these 3 ingredients fundamentally: topology, order, and interactions. We cannot ignore either of these 3 ingredients. And that also makes it a challenging. While this makes it a challenging theoretical problem, my task is to convince you that this is still a beautiful enough problem that we should attempt to solve it. Now, let me, in the next section, I will give you an overview, like some introduction to what these quantum Hall transitions are, why these 3 ingredients are important, and why the current theory, like the traditional theory, is insufficient to explain these transitions. And then in the last part of this talk, I will give you a dual description of these quantum Hall transitions, how that provides a good starting point, at least a better starting point than the conventional theory. Okay, so very briefly, the quantum Hall setup is roughly as follows. We have 2-dimensional electrons, in a perpendicular magnetic field. So their Hamiltonian is P minus A square over 2m plus dot dot dot. These dot dot dots can be interactions, impurities, and so on. And the capital A here represents the electromagnetic gauge field. So the curl of capital A is the magnetic field we apply. And as many of you are aware, that one gets Landau levels. So this is density of states versus energy. I'm just looking at this part of the Hamiltonian, which is a single particle Hamiltonian. And one just gets Landau levels, which are separated by cyclotron energy, h bar omega c. And each Landau level has degeneracy equal to number of flux quanta passing through the system. We will focus on filling fractions less than 1. So this Landau level, lowest Landau level will be partially filled. And this means all of the electrons have the same kinetic energy, and these dot dot, this first term goes away, it's just a constant, and these dot dot dots, the disorder and interactions, they become important. Now, the first ingredient, the topology, comes from the fact that each Landau level has a Chern number equal to 1. And if we have filling fraction nu e, suppose for now nu e is an integer, then the total Chern number of the system will be just nu e. And there's a relation between Chern number and Hall conductivity. I'm sure many of you are aware of this. Sigma xy is Chern number times e square over h. So that's where topology comes from. Now, how about why does disorder play a role? For that, we have to make nu e a fractional number. Suppose I deviate away from integer. I'm going to tell you why this is important. So we will have to look at the experiment. Let me first tell you how the experiment measures conductivities. So what one does is generally one applies a current, let's say in the y direction, and then measures electric field or voltage in the x and y directions. And then that's how we can measure resistivities in the experiment. Now, suppose rho xx is 0, then sigma xy is just inverse of rho xy. So that's one of the, it's a simple relation. Now, you can show that if we have translational invariance in the system, then this rho xy is simply inverse of filling fraction times h over e squared. And nu e, filling fraction, is a continuous number. So I should be able to, I should see rho xy as like, you can see that in this expression, magnetic field appears in the numerator. So rho xy seems proportional to magnetic field. So if I plot rho xy versus b, I should see a straight line. But in the experiment, one sees something very different. As I have already mentioned, that we see plateaus. Rho xy stays fixed in some range of magnetic field and then jumps. And what is this value where it stays fixed? It is actually 1 over integer times h over e squared. So in fact, nu e seems to be fixed to an integer. Now, to avoid confusion, I'm going to call the Hall resistivity, the nu e that appears in the Hall resistivity, as nu e prime. So generally, nu e in filling fraction is close to an integer, and nu e prime stays fixed at some value in some range of magnetic field. And then it suddenly jumps to a different value as we change the magnetic field. Let's say here to smaller value. So this is nu e prime equals 1, nu e prime equals 2 Plateau. And at this point, that's where our critical point is. And this is the integer quantum Hall transition. So this is completely, it's very different from the prediction of translational invariance. So we have to break translational invariance to understand these plateaus to begin with. And in fact, in the experiment, it is the disorder, random impurities, which lead to quantum Hall plateaus. And then the disorder will also lead to plateau transitions at this point. And as I have already mentioned, these are one of the best studied examples of quantum criticality in experiments.
So this is theoretical expectation that disorder leads to quantum Hall plateaus, or it is experimentally established fact?
So people have done scanning tunneling experiments on these transitions. They see that disorder is playing a role. They see puddles where you have large densities and puddles where you have small densities. So yeah.
But
I think
but it also can be achieved through contacts. It's open system with boundaries, so there is a contact where you connect wires.
Uh-huh.
And is this right? So maybe node is in the middle, in the bulk, but contacts. Is right.
You mean edges, conductors, or just like bulk system with
No,
contacts?
You connect to measure that you need to connect
right.
system, right?
Yes.
By wires through contacts.
Yes. But why would it be quantized through XY?
Yeah, that's what I'm asking.
I'm not
If the
sure.
translation symmetry is violated.
Oh, you mean the edges will break? The fact that we have contact at the edges, that will break
So
translation
this
symmetry.
is a
Yeah.
whole bar. And to do that, you have to connect wire here, wire there, and apply gates here,
Yes.
right? So it's there is no issue of translation symmetry, right? It's an open system
Yeah, but
with contacts. Would it be sufficient?
generally we think that edges should not be that important. It's purely bulk physics. As far as I know, the presence of contact is not.
For example,
Yeah.
the width of the plateau, how big is the plateau, right? It depends on impurities, right?
Yes.
So, but what about contacts? So if I consider contacts of different quality,
Mhm.
does plateau size of the plateau change?
Yeah, I'm not aware of that. Yeah, it does affect the transition. But let me tell you, in these transitions, very nice critical scaling is observed. You look at the width of this plateau transition, and it goes to zero as temperature goes to zero. So I'm not sure if contacts can do this. Yes. Yeah, but that's a good question. Yeah.
So the transition is, when is the criticality happening? Is that the transition or at
This
the
is the
plateau?
transition region. It's yeah.
Okay, but at the plateaus, the bound edge modes also have criticality, right?
But the edges only penetrate to certain distance in the bulk, and in the bulk electrons are localized.
Bulk is gap,
The bulk is it's not
not gap.
it's the mobility gap. So electrons would not move from one point to the electrons will not be able to move far enough, basically, in the bulk. But the density of states is still far enough.
So can I translate what you said into what is the theoretical expectation if I continuously reduce the impurity density or to zero? What happens to that to the state? What does it end up being, and how does it get there?
Thanks. So if we have infinite system size and zero temperature, any amount of impurities is relevant. And you will get exactly the same physics in the infinite size and zero temperature case. But if we have, because we have experiments not really have that, this width, this plateau region will actually broaden.
Yeah, but what I'm talking about is a theoretical expectation. The experiments see that. You are saying that what they see is due to impurities. Therefore, if I was able to reduce impurities, maybe it's not possible technically, but if I was able to reduce impurities, how would this evolve?
So
Does it evolve to that expectation that you gave on the left-hand side?
there's what?
So what is the expectation?
The expectation is that it will not change anything.
Hypothesis.
This order is relevant, so any tiny amount.
Even tiny amount.
Yes, the reason is this.
Okay.
Let me show this Hamiltonian. All the kinetic energy is quenched.
Can I comment on Mish's question? So to get this picture, you have to maintain chemical potential.
Mhm.
That's it. How you maintain chemical potential, there are many ways. This picture doesn't say. So if you maintain chemical potential, do whatever you wish, the picture doesn't change. This order allow to maintain chemical potential. Contacts allow, and there are 1,000 different ways to maintain chemical potential. It's a question of if you do ideal contacts, no disorder, you will not be able to maintain chemical potential.
Okay, but then why is the width of the step finite?
That's because of finite temperatures and finite system sizes. So you can, in experiment, reduce the temperature, or also you can also consider bigger samples, and the width of the plateau goes to zero, scales to zero in the. Yeah. Actually, there's one simple thing is to observe that all the kinetic energy is quenched if we project to the lowest Landau level. Consider cyclotron gap to be infinite, and then disorder is suppose there are no interactions, then disorder will be only term in the Hamiltonian, and that has no energy scale. So dimensionless. Yeah.
No interaction, we just ignore
Yeah.
interaction.
Let's ignore interaction for the moment. Actually, I will tell you about that's what people have been doing, and it's not sufficient. Okay, so disorder is important.
Sorry, maybe I can come. So quantum Hall effect, disorder or not disorder, it's happened. The question is how to measure it and present on the slide. That's for. So disorder is for, not to facilitate effect. Effects happened. Zero
I
disorder,
agree,
effect
but-
happened.
I agree, but that's not what this slide seem to seem to be pointing at, right? The message of the slide is that disorder is responsible for the
Yes.
quantization.
Yes,
Right.
I think, except for this contact issue, I'm not sure about the contacts. But if we have translational invariance, like consider system on a torus, in that case, we can show that rho xy should be a continuous function of mu e. So you have to break translational invariance somehow, either spontaneously or by disorder. And it seems in experiments it's the disorder. These samples are sufficiently, they are not very, let's say, not very pure. At least the ones that see integer quantum Hall effect on it.
So you're saying if I had a system where there was no disorder, but the translation invariance was broken anyway,
Yes,
you would still see the.
you could see,
quantum
yes. Wigner crystals could also give rise to a quantum Hall these plateaus. Okay, now the third ingredient, the strong correlations. Now, generally, these strong correlations give rise to more exotic phases of topological phases called the fractional quantum Hall phases. These experimentalists in the 80s made cleaner samples, and what they found was that they didn't just see integer quantum Hall state like this one, they also saw fractional quantum Hall states. So nu e prime is fractional, such as 1/3, 2/5, and so on. And these filling fractions are the prominent fractional states that they see. And as many of you are aware that these fractional quantum Hall states have fractional charge and anionic statistics and so on. And the role of disorder here is to give rise to these plateaus again. Otherwise, Wigner crystals can also do it, but these samples are sufficiently disordered. So it seems that strong correlations give rise to fractional quantum Hall state, but they may not be so necessary for integer quantum Hall transition. So this is the reason that
So what's the relation between the plots on the previous slide and the one 2 slides ago?
This is a cleaner sample. It turns out that the fractional quantum Hall states have smaller gaps. So you need cleaner samples, otherwise disorder washes them out and then turns them into essentially an integer quantum Hall state. Okay, so because at least the integer quantum Hall phases can be understood starting without interactions, the prevalent, like the conventional theory of these transitions uses only two of the three ingredients, topology and disorder. So this is a non-interacting electron description, and it maps onto a problem of quantum percolation. Now this can be seen as follows. Let's consider this Hamiltonian, v square over 2m plus some random potential v of r. And let's only focus on 1 to 0 transition, nu e prime equals 1 to 0 transition. This is an insulator, the right side, and the left one is the integer quantum Hall state. And let's consider infinite cyclotron energy. So we only need to focus on lowest Landau level. When we project onto the lowest Landau level, the motion of electrons is that they move along equipotentials of this v of r. So what we need to do is just look at any random landscape of potential and see how the equipotentials evolve as a function of the chemical potential or the filling fraction of the Landau level. So this is an animation which the red curves here show equipotentials, and we are changing the chemical potential in the lowest Landau level. So you can see that initially the equipotentials are very small, they are very localized, then they become bigger and bigger, they percolate throughout the system, and beyond chemical potential equal to 0, they again become smaller. So, so this is a problem in quantum percolation. And this is the critical point where these equipotentials are extended throughout the sample.
Sorry, what you have there, the equipotentials of the VR, right?
Yes.
What is the probability distribution of VR? What is the?
So this one I just took.
Generated.
So I generated it by taking Gaussian potentials of random sign and random strength. And I just considered them to be randomly located in space.
And no correlations.
No long range correlation. So it's not like V of R and V of R prime have 1 over R minus R prime to some power. It decays like a Gaussian at last distance, this correlation.
What is the typical correlation lengths?
Here I think might be 1 or 2 magnetic lengths. There's a length scale in the problem, the magnetic length, h bar over EB square root.
How does it compare with the size of that box, of that square?
So this box, yeah, I don't know, maybe it's 10 by 10 or something. I don't really remember. 10 magnetic
So
lengths.
it's much smaller than the correlation lengths.
Yes, the correlation length is very small.
How do you then create such connected regions? Is that?
Yeah, so it's a quantum percolation problem. So think of the usual picture is think of a landscape which has mountains and valleys. Start filling up this landscape with water. If we have very small amount of water, then we get small puddles, like small lakes. And if we have a lot of water, then we get oceans with small islands. So somewhere in this procedure, we will have a point where you will have both big lakes and big islands, essentially. And that's where this percolation happens. So this is the classical percolation picture, and it has a correlation length, which is roughly the size of the puddle. Now, what quantum mechanics does, it modifies this picture because now electrons have phases and they can tunnel from one equipotential to the other. And there will be many paths that the electron can take from one point to the other, and all those paths will interfere.
So just if I understand, so you pick your V, you
Yes.
pick a random distribution, put some Gaussian functions that simulate your disorder in the sample.
Yes.
And then you're increasing nu, so you're increasing the number of electrons, the filling factor, and there will be a percolation.
Exactly. And this is because of the, yeah, I explained that picture. You can think of that picture and that works. Okay, so this is a better schematic, I guess. In the case when we have filling fraction bigger than a half, so what disorder does, it gives a finite density it broadens the Landau level, and it instead of having a Dirac delta function density of states, we have a broadened density of states. So this y-axis is density of states versus energy. And if we are at chemical potential bigger than the center of this density of states, what we are going to get is most of the region will have new filling fraction 1, but there will be some puddles which have filling fraction 0. And this is essentially decided by those equipotentials. And on the flip side, on the right figure, we have most of the region is insulated, this brown region, and the sky blue region is filling fraction 1. So in both of these cases, one state dominates over the entire system. That's the one that percolates. So this state entirely is at filling fraction nu e prime equal to 1, because now we can support an edge state. On the other hand, this state will have no edge states, and this will be nu e prime equals 0 or the insulator. So this is how disorder is giving rise to these plateaus. It's creating small puddles which have 0 filling fraction and big percolated system which has filling fraction 1. And right at the center, at filling fraction half, you get these equipotentials which are extended throughout the system. And so there's then an effective picture which has been created out of this, an effective model, which looks at the saddle points of the potential, where two different equipotentials are coming close to each other. That's where tunneling can happen from one equipotential to the other, and quantum interferences can go through that. Yeah, phases of electrons. The wave function can, the phases enter, and then you get quantum interference effects. And this tunneling effects, they give rise to stronger delocalization compared to classical percolation. Classical percolation has some exponent 4/3. Here it will be different. So as I said, most of the physics takes place near these saddle points, and an effective model called Chalk-Coddington network model has been proposed, which just arranges these saddle points into a regular square lattice. People have tried modifying this a lot, but this seems robust. The universality class seems to be the same between more complicated and this model. So one can compute a localization length, which is essentially what is the probability that an electron injected here will arrive to the right side, and that probability reduces exponentially in the distance from here to here. And that's the localization length. And it goes like, near the transition, it will go like, it will have some exponent, nu. That's the correlation length exponent. And this can be done using numerics. People have found nu to be roughly about 2.61. Moreover, there's another exponent, which is dynamical critical exponent. This tells you how much time it takes to reach a localization length. And the density of states at the critical point is finite, as I showed you in the previous slide. And density of states has scaling of z equal to 2. So in fact, we get z equal to 2 in the theory.
So this can't be done analytically for, let's say, for some choice of ensemble of potentials.
So I think people have not been successful in solving that. There's another description where you average over ensembles of disorder, and one gets a nonlinear sigma model which describes these diffusing modes, and it has a topological term with a prefactor of pi. It's either +1, the phase is either +1 or -1, depending on the topological index of the configuration of these modes. But that's extremely hard to solve. Even for non-interacting systems, it's extremely hard to solve that problem. The reason is that the standard method of solving these is via dilute instant-on gas approximation, and it doesn't work with that approximation at the transition. So it's extremely hard to solve theoretically, but numerically, yeah, we can do it. As you can see, the accuracy of this exponent is really good. It's a very nice recent for numerical work. Now, let's compare this with experiments. Experiments are done on this two-dimensional electron gas. Let me not go into the details, but experiments generally measure the product of nu and z. And what they find is 2.38. Compare this with nu times z here, it's 5.2 on the non-interacting factoring model side, but experiments see 2.38. Moreover,
So this is which transition? It's 1 to 2?
it's 3 to 4.
3 to 4, the experiment.
The experiment.
And the theory doesn't care about.
Here it doesn't care because you can project out. You can, the Landau levels deep in the spectrum are gapped like they are at large energies. And dynamical structure fact, the dynamical exponent has been measured to be 1. This is somewhat controversial, but generally it's measured to be 1.
There's no error bar on the 1.
Yeah, ask the experimental. It's not a very accurate. Exponent, but it's closer to 1, maybe 10%, 20% error bars.
Do they measure this two exponents separately, or just this combination nu times z?
So actually, what is done is they measure nu times z in one experiment, essentially by scaling the width of the Plateau region, Plateau transition region versus temperature. And z is measured. So there's another experiment one can do which gives nu times z plus 1. And then we use the two data to figure out z. There's a separate experiment which measures z directly, but that experiment has been a bit controversial. But nevertheless, many experiments see z equal to 1 when you do these effective calculations. So it seems that integer quantum Hall transition requires addition of interactions. Simple
Sorry, and this result is all from simulations, right?
numerical simulations on this Chalk-Coddington model, on this network model. Now, there is another reason why we are interested in these interaction effects, because we don't just have integer quantum Hall transitions, we also have transitions between fractional states, like 1/3 and 2/5. So this is an experiment that was done in the 1990s. They measured 1/3 to 2/5 transition. The exponent of that, nu times z, is 2.33. And you can see it's very close to the integer transition, 2.38. So it seems that fractional and integer transitions both have the same critical exponents. Moreover, there's another quantity. At the transition, we get gapless degrees of freedom, and they can dissipate energy, so you get some non-zero rho xy. Rho xy, otherwise, there's no dissipation in the phases, but there is some dissipation at the critical point. And rho xx at the critical point is h over e square for both an integer transition, 1 to 0 transition. So some of these points are 1 to 0 transition. I think the empty points are 1 to 0 transition. And these field points are 1/3 to 0 transition. And rho xx in both transitions seems to be close to h over e square. These two facts, that exponents are similar and critical resistivity is also similar, these two facts have led to a conjecture. This is a conjecture from 32 years ago. Actually, it was the year I was born, so it's quite old. These have led to a conjecture of super-universality. What does this mean? It means that fractional transitions and integer transitions are in the same universality class. But we did not have any arguments for why theoretically this could hold. I will give you one argument. It's not airtight, but still something interesting. And so this means that interactions are fundamental at quantum Hall transitions, and it will be nice to have a unifying framework for studying all these transitions in one theory, as opposed to having a different theory for fractional transitions and integer transitions. So this is where this dual description of quantum Hall transitions comes in. We already have a unifying framework with two different ingredients. So eliminate disorder and just consider topology and interactions. And we have a unifying framework in that particular case, and that's called the composite-fermion framework. These composite fermions are electrons attached to two flux quanta. So we attach two flux tubes to all electrons, convert them to these emergent degrees of freedom. And this framework is quite powerful in the sense that it converts the strongly interacting fractional quantum Hall phases into integer quantum Hall phases. So what we need to do is, to study Plateau transitions, we need to add disorder to this framework. And I will explain how disorder behaves in this theory, and I will give you a starting point and give you some predictions or some guesses for the fully interacting theory. Okay, in this talk, I'm going to use the Dirac fermion version of composite fermions. This was proposed by Son in 2015. So in the top line, I have Dirac electrons in the 0th lambda level. So capital A is external gauge field, capital psi is the electron operator, and these dots again represent disorder and interactions. We can attach two flux quanta to this theory and dualize it into composite fermion theory, where we have little psi, that's the composite fermion, interacting with an emergent gauge field little a, and then we have these cross Chern-Simons term, little a d capital A. And the curl of capital A, I'm going to call them magnetic field, external magnetic field, and curl of little a, that will be emergent magnetic field. And let me just explain to you how this composite fermion perspective converts the phases into weakly interacting, or at least at some level, weakly interacting phases. Let's consider filling fraction 1/3. Here I have one electron and three flux quanta coming from the external magnetic field. If I attach two of them to the electron to form a composite fermion, the red one is composite fermion, then I'm left over with one flux quantum and one composite fermion. that's in fact the integer quantum Hall state of composite fermions. So I've converted 1/3 into a filling fraction 1. Similarly, 2/5 state can be converted into filling fraction 2 for composite fermions. So 2 Landau levels of composite fermions are filled. Now this is seems something trivial, but I'm going to focus on this particular case. Suppose I have only one net flux quantum per electron, that's filling fraction 1. Then I attach 2 of them to electron to convert that to composite fermion. The flux quantum just reverses its direction. So it is in fact filling fraction -1 of composite fermions. And at half filling, that's where this transition happens. There I have 2 flux quanta per electron, and then there's no leftover magnetic field for composite fermions. So composite fermions they don't experience magnetic field. If we did not have any disorder, they will fill up a Fermi sea. Okay, I just need to tell you these two duality equations. In this new theory, the electron density, you can figure it out using this derivative. It's external magnetic field minus emergent magnetic field by 4 pi. Now, external magnetic field is fixed. So electrons are essentially emergent flux quanta by 4 pi. The magnetic field by 4 pi, emergent one. And the composite fermions are at finite density. That's important. So the composite fermions, the number of them is just given by external magnetic fields by 4 pi. And this equation comes from looking at the equation of motion of little a, that little a imposes a constraint. So we just need these two equations. And now let's add disorder to this theory to obtain a description of Plateau transitions. The motivation here is that some interaction effects have already been taken into account because we can convert fractional quantum Hall states into integer quantum Hall states of composite fermions. So let's first just analyze mean field theory, where we ignore the temporal fluctuations of the emergent case field.
Just a nice question. So here, nu equals 1/2 is going to be the transition. You're going to view it as the transition between integer. So you're kind of going to ignore possible fractional.
Yes. If
states.
disorder is sufficiently strong, then it washes out fractional quantum Hall states. And in fact, it turns out that if you think about the phase diagram, extremely close to half filling, the transition actually, you get reentrant nu equal to 1 and nu equal to 0 phases. It's somewhat of a subtle point, but it is always 1 to 0 transition at half filling in the presence of disorder. Okay, so let me ignore temporal fluctuations, but I will have spatial fluctuations because those will come from disorder. Now, a random potential in the electron side will create a random density of electrons. Remember that puddle picture I showed you, which had some regions of 0 filling fraction, some region of 1 filling fraction. So now, because in the composite fermion perspective, electron density is given by the emergent magnetic field, this means I'm going to have a random emergent magnetic field that will be experienced by the composite fermions. So I can write down a mean field Hamiltonian. This is just the Dirac fermion, the composite fermion, which experiences a spatially varying magnetic field, this little a. Little a has no time dependence, only spatial dependence for now. And because we have finite density of fermions, there's a finite chemical potential. So here, it's good to divide this magnetic field piece into two distinct pieces. So one of them is the average magnetic field, average emergent magnetic field experienced by composite fermions. And this is a tool to tune away from half filling. You can see this via this equation, like B naught average piece of this B of R is 1 minus 2 times the filling fraction times the external magnetic field. If I tune away from half filling, I will generate an average magnetic field. But then there is a random piece, B tilde, which is disorder, and that will remain fixed. It will be random, but it will remain fixed for a given disorder realization, for a given sample. So B naught is variable, but B tilde is fixed, and its average is 0. Okay, is that clear? Now, let me ask this simple question. can we reinterpret the electron transition from 1 to 0 in these new composite fermion coordinates? In fact, the answer is yes, and the description is quite robust. And as I will show you, the robust description comes from the fact that Dirac Hamiltonian in random magnetic field has 0 modes. It also has parity anomaly. And we will also use Lafrenz gauge argument and see that this description emerges. Okay, so let me tell you about the first ingredient, that Dirac Hamiltonian in a random magnetic field has 0 modes. Essentially, that's just, you look at the Hamiltonian and there are some wave functions which are annihilated by the Hamiltonian. And this is an index theorem, Atiyah-Singer index theorem, which tells us the number of 0 modes is the total number of flux quanta passing through the system. These are emergent flux quanta. And this is true even if we have a random magnetic field. The number of 0 modes is fixed. So if you were to look at the density of states of this Dirac fermion Hamiltonian, if B0 is bigger than 0, that corresponds to filling fraction less than a half, we get some 0 energy modes, the red line in this plot. And if we have, again, B0 less than 0, or filling fraction bigger than a half, we again get these 0 modes. But right at B0 equal to 0, or filling fraction half, that's where this transition happens, there are no 0 modes. And there is sort of an average time reversal symmetry because magnetic field is random. So there is an average time reversal symmetry. And remember that we have finite chemical potential, μCF. So if I were to look at only the Hall conductance that comes from these 0 modes, it turns out that these are very analogous to the 0th Landau level of Dirac fermions in a constant magnetic field. So they have the same Hall conductance as the 0th Landau level of Dirac fermions in constant magnetic field. So in this left case, the Hall conductance that comes from purely the 0 modes, it will be E square over 2h. And in the other case, this right side will have minus E square over 2h Hall conductance. That's because B0 is negative. That's why we have this minus sign. And right at the transition, because we have an average time reversal symmetry that sets the Hall, and there are no 0 modes actually, so it sets the Hall conductance of 0 modes to be 0. Is that clear? These 3 things. Okay, now the second ingredient here is that single Dirac fermion in 2 dimensions is anomalous. It's not regular under large. It is not partition function basically is not invariant under large gauge transformations. To regularize it, we have to add a massive Dirac fermion. And what I'm going to do, I'm going to add a massive Dirac fermion. You can see its density of states is shown here. I will take the mass to be infinity, and the chemical potential is fixed at some finite value. What it does, it doesn't alter any low energy physics. All it does is shifts the Hall conductance of that comes from the 0 modes by minus E square over 2h. So this picture from the previous slide, it converts into this right one. We get 0 Hall conductance from these 0 modes at V0 positive, at V0 bigger than 0 or filling fraction less than a half, and then minus E square over h, which is the integer quantum Hall state for B0 less than 0. And right at the transition, we get minus E square over 2h. So if we only looked at 0 modes, we did not worry about what positive energy states are doing or negative energy states are doing. We would see a quantum Hall transition between filling fraction 0 and filling fraction minus 1. Now, what are these positive and negative energy states doing? They are not doing much. And the reason is that in 2 dimensions, states, the electron states, they like to localize in the presence of disorder. Unless there is good reason, like topology, they will always localize and will not contribute to Hall conductance. And this is basically what is encapsulated in this 2-parameter scaling. Let me just give you the result in the interest of time. So if we had filling fraction less than a half, then we have Hall conductance bigger than, more positive than minus E square over 2h. Some of that actually is contributed by these 0 modes. And some of that might come from positive energy states, but it will be bigger than minus E square over h no matter what. And under RG flow, this will flow to sigma xy equals 0. This is, importantly, this is composite fermion Hall conductance and not electron Hall conductance. We need to distinguish between the two. Similarly, on the other side, we will have composite fermion Hall conductance less than minus e square over 2h or more negative than that. And under RG flow, this will flow to an integer quantum Hall state with minus e square over h Hall conductance. And both of these have localized states at the Fermi level because Fermi level is at finite chemical potential. So all those states are localized. Importantly, the zero modes cannot be localized because they are some exact wave functions of the Hamiltonian. And right at the transition, you can show that all the states at the Fermi level must be extended. So there are no zero modes, but the positive energy states are no longer localized. They are all extended states. And this is the transition point. Now, okay, this story is quite robust. We have verified this using analytical arguments, numerical simulations in both continuum and tight binding model. But let me just summarize it with this one line, that the transition in the electron side between 1 and 0 states has been mapped onto a transition from -1 to 0 states for composite fermions. This is essentially a summary, the one-line summary that you need to know of the previous discussion.
The sigma XX, what will you talk about?
Sigma XX.
It looks like there's a.
At the critical point, it's finite. So at the critical point, all the positive energy states, actually, the entire spectrum has extended states. They are not localized. They have finite sigma XX.
And this you compute in the kind of free Dirac theory on the free Dirac side.
Yes, free Dirac side, you can show it is extended. This has been done numerically, like quite extensively. Okay, so with this conclusion, let's see what we can do. Actually, let me skip this slide in the interest of time. For now, it seems somewhat a trivial exercise. We have converted one integer quantum Hall transition to another using dualities. Let's now ask what it can buy us. What it buys us is a description of fractional transitions. So now let me look at the transition 1/3 to 0. If we attach two flux quanta, it maps onto actually 1 to 0 transition. Remember, the 1/3 maps onto 1 filling fraction for composite fermions, and 0 maps to 0. So it has mapped to exactly the transition on the left side in the first line. So all I need to do is attach two more flux quanta, and it will convert 1/3 to 0 transition into -1 to 0 transition, exactly the right side. And in this way, we can convert all abelian fractional quantum Hall transitions into the -1 to 0 transition of composite fermions, of these emergent fermions. So this should remind you of that super-universality prediction from the experiments. But this is for now only a mean field level super-universality. I mean, we can map everything to the same transition, so that hints towards super-universality. But this is only mean field because we have not analyzed the effect of emergent gauge field. I had ignored the temporal fluctuations of the emergent gauge field. Actually, at the mean field level, some of my collaborators are recently finding that indeed this super-universality holds. So that story is airtight. But we need to go beyond mean field theory to understand what happens to super-universality and also dynamics. So one thing it buys us, so let me tell you what the gauge fluctuations actually look like. Suppose we have Coulomb interactions on the electron side. That looks like this. We have two particle potential, U of Q, and this is density of electrons square. Recall that density of electrons is essentially emergent magnetic field by 4 pi. So it converts into this term, the second line. And then if we choose transverse gauge, where this divergence of A is taken to be 0, we can write emergent magnetic field as Q times the transverse gauge field. So this is the term that appears in the Lagrangian, that is the gauge fluctuations, that gives rise to the gauge fluctuations. And U of Q, suppose we had Coulomb interactions, it will be G square over Q. G is the strength of Coulomb interaction. And if we had short range interactions between electrons, like if we screen Coulomb interaction, we will have some constant. Notice that these gauge fluctuations vanish if I take G square to infinity. that makes the energy required to create these gauge fluctuations infinite. And this is different from electron description. If I wanted to get a non-interacting electron description, for that I will need G square equal to 0. So you can think of composite fermion and electron theories being in different at different strengths of interaction. Like one is at G square equal to 0, the other one is at G square equal to infinity. So what happens when we add these gauge fluctuations? Now we have not solved the full theory, but we can make some general predictions. So one thing is that let's integrate out the fermionic side, and what that will do at the critical point, it has a finite sigma xx at the critical point. So if we do that, then the transverse gauge field, its propagator gets modified with this first term, and we have the second term that comes from Coulomb interactions. Now, if we have Coulomb interactions, U of Q is 1 over Q. So omega goes like Q for Coulomb interactions. And that's where Z equal to 1 comes from. Omega goes like Q in this. Essentially, this is an effect of Coulomb interactions on the density fluctuations in the system. If I did not have interactions, and I create a density fluctuation in the system, it will relax by random walk, and that gives rise to diffusion with Z equal to 2. But if I had Coulomb interactions, these density fluctuations will experience an outward Coulomb repulsion, and that will make it relax faster. And that's what leads to Z equal to 1. And if you have short-range interactions, U of Q is constant. In that case, omega goes like Q squared. We get Z equal to 2 for short-range interactions. So this is one thing that this description buys us. There is a second thing that it also buys us super-universality. As I have explained, all the transitions can be mapped onto the same transition in the composite fermion language. And in fact, the only difference between different fractional quantum Hall and integer quantum Hall transitions is that there is a Chern-Simons term for the emergent gauge field. So this first green term, which has a coefficient of lambda, that's the only difference between different transitions. Now, because there's finite density of states at the transition, that leads to screening, and that produces the second term. It screens the temporal component of the emergent gauge field. Now, suppose I integrate out the temporal gauge field, then what happens, I only get a term for the transverse gauge field. And this lambda term appears with a factor of Q squared. And you can see that this first term is small compared to the second term in the long wavelength limit if U of Q is Coulomb interaction. If U of Q is 1 over Q, and this goes like Q, the first term goes like Q squared. This means that the Chern-Simons term is unimportant if I have Coulomb interactions in terms of electrons. So there will be super-universality when Coulomb interactions are present. Although we have not solved the full theory, but it appears that we can still make predictions, arguments for the super-universality. On the other hand, if we had short-range interactions, this U of Q was like constant, then the first and second term both are of the same order, then the Chern-Simons term is marginal, and then super-universality may not hold. So this is something that experiments can try to do. They can try screening the interactions to short range and check if they still get the same critical exponents, same critical resistivities in the experiment. Okay, so this is a summary of this composite fermion description. We have found some robust interaction effects, such as integer quantum Hall and fractional quantum Hall transitions should have the same exponent, and Z is 1. And this is supported by a nonlinear sigma model approach. I would not go into this, but we have some theoretical basis for supporting these statements. Moreover, we have computed the critical exponent in the limit G square goes to infinity. That's where free composite fermions arise. And this critical exponent is 2.56, which is very similar to the Chalker-Coddington exponent. However, we need to add gauge fluctuations to improve upon this critical exponent, and that's part of the future in this field. So this is, you can take this back from this talk, that When we have no Coulomb interactions, then we have a description in terms of free electrons. When we have extremely strong Coulomb interactions, then we have a description in terms of free composite fermions. The question is what happens to these 2 points at these 2 extremes when Coulomb interactions are finite? Is there a point in between here at finite G square that controls this transition? Or are these 2 different limits which are stable? This problem is not solved so far. Okay, so let me mention some future directions in the next few minutes, and then I will finish. The main challenge is to include gauge fluctuation effects at the quantum Hall transition, where sigma xx is of the order of e square over h. We have techniques for doing this when sigma xx is very large, but we don't have good techniques for doing this when it is of the order of e square over h. And we have a mean field critical exponent. One of the projects I'm thinking of in future is let's include gauge fluctuations, maybe only at a Hartree-Fock level, and we can ask what happens to nu, and does this description stay robust under at least the Hartree-Fock level analysis of interactions. We have also been recently thinking about construction of network models for fractional quantum Hall transitions. Essentially, take that Chalker-Connington model picture of equipotentials, and instead of having fermions on those equipotentials, one can have anyons moving on those equipotentials, and they will then scatter at the nodes from one equipotential to the other. And then we can ask the question, are fractional quantum Hall transitions any different from integer quantum Hall transitions when anyons are hopping across the saddle points? And this will be a good description when we have short range interactions between electrons. Moreover, for the dynamics, one can look at time-dependent numerical methods and verify whether z equal to 1 scaling really holds in the numerics, or so one can verify the nature of dynamics. All right, let me finish there. If there are any questions, I'm happy to answer those questions. Questions?
Yeah, so you said your computation for nu, the critical exponent nu, will require incorporating gauge fluctuations. But why are you confident about your result for z? You said z is 1 or 2. This won't get.
Yeah, thanks. That's a good question. The reason is that this argument only requires composite fermions to have a finite sigma xx. And as long as that is true, I mean, it will be very strange to.
So the sigma xx should really probably be a scaling function of omega over q squared or something if they're diffusing.
So it will be the important thing is that it should go to a finite number in the long wavelength.
Yeah, but why are you taking q to 0 first in that number? Right, it's probably some scaling function of omega over q to some power.
Yes.
And somehow you're saying the right thing to do is to take q to 0 there.
Exactly.
Presumably because I guess you're assuming something about u of q that it.
Not necessarily. It's just a general argument that the DC conductance is finite at the transition because there will be countless degrees of freedom.
Mm-hmm.
I mean, at the mean field transition, sigma xx is roughly e square over 2h. And it will be, it's hard to imagine why that will either go to 0 or infinity.
Yeah, this I agree with, but I wonder if there could be a correction. Okay, maybe it's benign, but like let's say sigma, I write it as a constant plus q squared over omega.
Yes.
And I guess I think you're saying we can ignore that because u of q is either
Q
a
is small.
constant.
Yeah, q is 0. We take q to 0 first, and then omega to 0.
Yeah, but if u was constant, you'd have another q squared, which you are keeping track of.
Yeah.
Right. But I guess that's the point. U is more singular. Yeah. Goes
for
to
Coulomb,
yeah.
for Coulomb case, it seems.
For Coulomb, it seems safe.
Yeah, that's actually a good point. Maybe for short range interactions, things could be more complicated.
Well, it just seems to marginally be okay. Maybe so. Yeah, maybe it's fine.
Yeah, but people have claimed to see different exponents, different z than 2 for short range interactions. So it's possible. Yeah. For Coulomb, we can be more confident.
Sorry, but now I'm confused. For Coulomb, there you get z equals 1, right?
Yes.
When would you get z equals 2? Like
for short range interactions.
Sure. Yeah, U constant or something.
And we screen interactions using gates or something.
questions? Thank Prashant again.